It's my pleasure to introduce our speaker today, Dr. Chris the Manimal Polashenski. Chris is a research geophysicist at CRREL, the Cold Regions Research and Engineering Lab. And he spends his time split between working here in the Upper Valley, and also he spends a lot of time in Fairbanks, Alaska, where I think he's headed tomorrow. So he did his undergraduate work here at Dartmouth. He also did his PhD in engineering here at Thayer, graduated in 2011. He is the first graduate of the IGRT program in polar environmental change, and we're really excited to have him here today to talk to us about some of the research he's been doing trying to understand energy balance on the Greenland Ice Sheet.
All right, thank you very much. Great crowd. I was expecting like 5 people in the room right after the holidays, so I'm glad to see so many faces here. I was told that I should share some research and also some profound insights about what it's like to be in the science workforce after the IGRT program. I don't think I have that much profound, but I'll see what I can do. So I've been working on a few different projects, but the one I want to talk about today is this project called the SAGE project, Sunlight Absorption on the Greenland Ice Sheet. And the overarching goal of this is to understand why there's changes in the albedo, or sunlight reflectivity, of the Greenland ice sheet. What we've been seeing over the last couple of years with increased melt on the ice sheet is that there's a lower albedo, which means that more sunlight's being absorbed on the ice sheet. And albedo is a pretty simple concept. It's just the amount of sunlight something's reflecting. It varies from 0, which would be an object that absorbs all the light that hits it, it's completely black, to 1, a perfectly white object. And I put a couple of little marker points on there for fresh snow, which is like, this is the beautifulest, pristine white snow. That stuff we had just a few days ago would have been around 0.9. 90% of the sunlight that hits it reflects. Snow that aged a little bit, that was a couple days later, would be 0.7 to 0.8. Melting snow, that stuff that we had out there over the last yesterday and today, would be 0.5 to 0.65. And then on the Greenland ice sheet, you could get down to exposed ice or water-covered ice. So you can vary a really wide spectrum of albedo, which has a really profound influence on how much energy is being delivered to the ice sheet. And interestingly, as you look at these, the lower the albedo, as you go through that spectrum of different surface types, that's the more melting is occurring. So there's a potential for a positive feedback cycle here, where you warm it up a little bit and it moves from fresh snow to old snow to melting snow, which causes it to absorb more sunlight, which continues to move it this way down the spectrum. There's other things that affect albedo, though, on the ice sheet, or anywhere around here, too. And we can see them in spades out here along the road. It's not just dust here, it's that stuff that they spread on the road, whatever that might be. It can be that blue salt we have over in Norwich, or it can be the sandy stuff that the college likes to mix up. But you can in Greenland, you're far away from the road spreaders, so you have some different contaminants that get there. Black carbon, which is from fires, burning biomass in nature, or diesel engines and coal-fired power plants from the anthroposphere. Dust from faraway deserts can blow there, and volcanic ash can blow there. All of these things in the ice can make it darker, just the same as those changes in the character of the surface. One of the ones that's really the most powerful at darkening the ice sheet is black carbon. And in round numbers, somewhere around 20 parts per billion of black carbon, a very, very small concentration, can darken ice by about 1% albedo. And so if you have 300 watts per square meter of incoming sunlight, 1% of that would be an additional 3 watts per square meter. That's on the order of the same magnitude as the effect of the rise in CO2 over the past couple centuries has been. It's around 2.1 watts per square meter. So you could do something significant if in fact you were getting some high concentrations of black carbon up there. So we came up with this plan to try and understand which of these various aspects are causing changes in the albedo on the ice sheet. And Zoe Courville, who's I saw in the room, there she is. She changed her jacket. She was green before. And is the lead on this proposal. We proposed it together in 2011 to go along with the GRIT traverse, which is the resupply traverse that moves fuel from Thule Air Force Base and supplies up to the major ice camps on top of the ice sheet, the Neem drilling camp and to Summit Station, and to do some work along the way measuring albedo and measuring the things that are changing albedo or influencing albedo. We came up with a set of objectives that we would do. We figured along the way we'd hit 20 sites on that route. We'd measure the albedo to see what it is, and then sample for the things that change albedo, those black carbon dust and tracers to figure out where the black carbon and dust came from, and the snow grain size to figure out how much the snow, its character itself, is influencing albedo. And we'd put out some autonomous stations that would track albedo over time so we could see how it was changing month to month when we weren't there, because we only got that one drive from Thule to Summit to take a look at it. And surprisingly enough to me, somebody bit and it was funded. So then we had to actually figure out how to do the work. And shortly after the time we got it funded, we got some bad news, which is that budget cuts canceled the GRIT Traverse for 2013. There'd be no resupply traverse to go on. I think that the program manager really had us dialed pretty well, though, because on the phone call to tell us that the traverse was canceled, they waited just long enough until we put our foot in our mouth about how upset we were about that before telling us we could have 3 snowmobiles and all the gas we could burn in order to execute the project anyway, which sounds a lot more fun to me than going along with a big heavy traverse that has its own schedule and doesn't want you to be doing science at all hours of the day and night. And another very interesting and good for the science perspective thing that happened was that there was a really unusual event on Greenland. A typical year for the last few years on Greenland, melt is confined to these red areas around the periphery of the ice sheet, and up in the interior of the ice sheet you don't get any melt at any point during the season. In 2012, it melted up and over the entire ice sheet, so the entire ice sheet experienced melt. That's kind of unusual. In the ice core record, there maybe are a few other times that happened, but it certainly doesn't happen very often. At the same time as that happened, there's some folks who are working on checking out what the albedo is using the MODIS satellite. And they've tracked the albedo over the course of this season. This is the day of the year at the bottom, and for translation, here's the months: March, April, May, June. And the albedo every year, as it goes from that really dry, beautiful, fresh snow, and this is all up in that area that doesn't usually melt, the grain size grows as it warms and gets to older snow, and the albedo drops from 85% here to about 75 to 80%. And it varies from year to year a little bit, but what really stands out here is that 2012, that year where something very different happened, the albedo was actually quite different. It seems to kind of go down in a step and then hang out there, and go down in another step and then hang out there and then go down in another step. This one here is easy to explain. That's when it started melting. So we went from dry snow to wet snow. But these ones here, it wasn't actually melting on the surface yet. Something lowered the albedo prior to it starting to melt. We've got 2 candidates from the talk so far. One, the grain size of the snow grew, and the character of its surface was simply different. And the other could be that some additional contaminants, black carbon or whatever, was deposited on the surface. So that provided a really neat motivation for going to check this out. And at the same time, in 2012, there were some really big events elsewhere in the world. In Siberia, there was a record-setting year for wildfires. About 73 million acres burned, where a typical wildfire season is an order of magnitude smaller than that. So it was a year that an awful lot of smoke was put into the atmosphere. And this is the MODIS product showing the intensity of fire. And you can see this area in Siberia here, which is burning quite a lot. Now, Africa looks like it's also on fire quite a bit, but that's not so unusual. Those are grasslands that tend to burn in most years. This is a boreal forest that has a burn cycle that's much longer, 40 to 75 years. So seeing that intensity of burning going on, this was an unusual event, and perhaps could be sending an unusual amount of black carbon over to Greenland. So some modeling happened, and we could see that, in fact, some of those smoke plumes should have moved over Greenland based on the reanalysis of weather patterns and movement of air masses. And in fact, also you could see some of these smoke plumes. This is not reproduced very well on the plot here, but this is a plume of smoke seen from a MODIS photo. And then you can also do a track across it with the cloud lidar, Calypso, and you can see the smoke, which is differentiated from water vapor in the clouds here based on its polarization. You can see that smoke as it moves around Earth. And you can even see that some of that smoke went over Greenland ice sheet. This is the smoke plume right here. And you can see that some of it was in contact with the Greenland ice sheet, which kind of sets all the stage for, and was reported widely last fall, that perhaps this big melt event happened because these wildfires in Siberia emitted a little bit of extra black carbon. It made its way over to the ice sheet, got deposited on the ice sheet, darkened the surface, caused more sunlight to be absorbed, and caused the ice sheet to melt. It's a neat story, and it would be awesome if it was true, because it would probably be a Nature paper. So we figured we'd go check that out. So you know, here's the schematic would be, well, we have more wildfires, we get a additional melt on Greenland. The cool thing about this is that the link here from additional warming on Earth to more wildfires is actually something that's becoming somewhat better established as something that you can see in the paleoclimate record. So if more warming makes more wildfires, and more wildfires make more melt on Greenland, and more melt on Greenland probably feeds back to more warming, this could be a long-term feedback cycle that would accelerate climate warming. Just a possibility, no proof there yet. So once you've got an idea like this, we figure if you had a movie being made, the next scene would be like us tearing off across the ice sheet, wildly sampling, like leaning off the sides of the snowmobiles to gather this, and you know, within, I don't know, 15 seconds afterwards, we'd have a conclusion. In real life, it works a little bit differently. The next scene in real life is an awful lot of paperwork. And I work at CRREL, which is part of the government, and we may have more paperwork than other places. But you could make 4 or 5 of these kind of slides anywhere you worked. It takes a lot of work to get the permits together, to get the plan together, and to get ready to go. And beyond all the paperwork, you also have to just think about practical things like how much gas do we need to drive from Summit Station up around this route. And I think when the program manager offered us 3 snowmobiles as a consolation prize for not having the grit traverse go from Thule to Summit, I think what they intended for us to do was to drive a little bit around Summit Station and collect a few measurements. But I don't see why you would do that. So we decided we'd actually do the entire route, and then since nobody was telling us what to do, we would also add a route up that direction and see how much of the ice sheet we could sample to understand the spatial distribution of how black carbon was getting deposited on the ice sheet. Whether there was interesting things like there's a continental divide here, is there less on the back side of the continental divide and more on the front side of the continental divide, and different areas of deposition on the ice sheet to try and sort out how it might have had an impact on the ice sheet. Once we had our plan, we kind of started working on what we would eat, and I thought we were over planning a little bit. You know, being out 40 days, for example, having 83 pounds of chocolate seemed like maybe a lot with 3 people. That would be, you know, 2 pounds for 3 people every day. Well, we ran out. Mike and Nate, the two gentlemen we hired to go along on this trip, have astounding appetites in the cold. I thought I was doing pretty respectable, putting away 6,000 calories a day. Nate thought he was doing pretty well, putting around 8,000 to 9,000 calories away a day. And Mike was really dominating at about 12,000 calories a day. And so we you know, there's a lot of these practical things. I mean, being a scientist is not just about getting the data and going to your laboratory and hiding. It's about getting yourself prepared for the field in such a way that you can spend the maximum amount of time actually doing the work and being comfortable. None of these trips are about the adventure in my mind. That would be what Scott would have said. I prefer to think like the Amundsen way. You're supposed to be like, wow, going to the South Pole was a neat little ski, and we got some data along the way. And so the more you can prepare in advance, the better off you are. And this was one of my favorite prepare in advance things, is that in my kitchen last spring, we made up a whole bunch of little burrito-like things, and we made little cookers and put them on top of the mufflers of the snowmobile so that while you were driving, you could prepare yourself a hot lunch. And assembling a team, also another very important thing, critical for making it so that you can have a good time and get good science done out there. I had a little bit of a hard time finding a good team. You have to bring in a bunch of different people and see what they can handle. And I recommend good interview processes. And the interview process for going across the Greenland Ice Sheet was showing up in Fairbanks and going on a hellacious ski through an alder swamp with me while I pretended to get lost. And if you were still happy, as Mike was like, wow, this alder swamp is really neat, and these trees, I've never seen structures like this that are so impossible to get through. Then you win, and obviously are capable of going across the Greenland Ice Sheet. We spent a lot of time working with, again, more mundane aspects of our gear, making sure our snowmobile sleds were right, getting the hitches just so we could change loads around as we were going, planning to make sure that we can fit all this stuff in the sleds, and making diagrams of all the sleds and where all the weight would go and things like that, taking snowmobiles out in Fairbanks, loading them up to the same weight, seeing if they would go. And for reference, they do go, but only if you're off the seat pushing next to the snowmobile while you're getting it started. Then they go great once you're rolling. And then, of course, the most important thing of all, coming up with an acronym. You have to think for a while to come up with the best acronym. And we in the end, determined that SAGE has a good ring to it. It feels academic. And sunlight absorption on the Greenland Ice Sheet, it's descriptive. And we have to go with that ultimately. But some of these were a lot better, actually. And this is the edited version. And all this ordering and planning and getting everything together, a month or so before starts to come together, and all the gear comes in, and you have Christmas in the warehouse, and feverishly start putting together. These are the stations we put out to continuously monitor albedo on the ice sheet. And had a lot of really good help at the last minute. And this is one of the things I'm supposed to give profound insights. Be really, really nice to all your support staff. You can't get anything done without them. They can make your life very, very easy, or if they so choose, very, very difficult. And I had, in the last minutes of getting ready for this trip, I had amazing support from everybody across the board who kind of got that this was important and this was something that was really important to support. So that was getting the stations built and then getting it packed and shipped out. And we have some great shipping people who did that. And then a team of people who helped us arrange travel and travel orders and physicals and everything like that to get ourselves up to the Greenland Ice Sheet with our gigantic pallet of everything we needed to live on the ice sheet for the next 7 weeks. We've double-checked our rations, make sure we've got everything we need. Important thing in the cold is to make sure you have enough butter to stick in whatever you're eating. And then nothing in the field ever goes the way you planned it to, ever. And one of the best things to be ready for is how to figure out how to get around those obstacles. We ended up having a little bit of a problem in that, in programming language, diesel not equal to gasoline. All the barrels that we got for fuel were actually contaminated pretty badly with diesel fuel and water. And the snowmobiles didn't like that very much. And so we had a few-day delay of game trying to get out of Summit Station. And it was relatively stressful, as Zoe might attest to. But after a little bit of repairs and maintenance and some grim faces made, we were ready to go. We got it all together, put everything in, and finally we get to the scene in the movies where we're off. So the unsupported nature of this, we didn't have a heavy traverse to work from, meant that Zoe got to come up and go for a 350-mile out and back to drop off all the fuel that we would need for the traverse because the machines were going to be too heavy. And then we went back down to Summit Station to get all the science gear to actually go out on the traverse with Mike and Nate. So this is something I found kind of comical. I went back in my email and figured out when the first email Zoe sent me about this idea was, and I also got the first measurement that came back from the station and figured out that it was 568 days, 14 hours, and 5 minutes between the idea and the first actual piece of scientific data that came in on this. I guess that just says that it takes a lot to get one of these things off the ground. After we got out there, we got our first station out, we started doing things. It settled into a routine pretty quickly, and because of all those preparations we'd done, it was pretty easy. We had everything we needed. We had all of the backup gear and equipment to repair everything that we broke, and it was a good trip going along. So at each site we would pull in, we would dig a snow pit, we would measure the albedo at the surface of the snow, and then we would measure for contaminants down through the snow and check the grain size of the snow down through. We would also do a couple other things, because while you're there, you might as well do a couple other things, one of which was to drill boreholes down to 10 meters to measure the temperature in the ice sheet, because that was something that was done by a prior researcher in the 1950s along this same route, and we could compare those data that he took to what's going on now to see how the ice sheet has changed in the last half century. These are pictures of us measuring the grain size on the ice sheet. I guess I'm running out of laser batteries here. Going through the process of sending out our daily blog post, measuring albedo on the surface, and taking samples for later analysis for black carbon and chemical species that would indicate perhaps where that black carbon had come from. Along having a routine like this, there were a few interruptions, but nothing too major. I mean, the generator seized and we had to take it apart and put it back together. We found that melt in 2012 was actually sort of pesky because we had anticipated to be shoveling snow, and so we'd brought shovels. Shovels are very good for snow. Solid ice, however, is not very conducive to being shoveled with snow, or being shoveled with just shovels. We should have brought pickaxes, and we didn't. So that's someone's hand there. These are about 7 or 8 inch thick layers of solid ice that we found in a lot of the pits. And as we got closer to the coast, we actually found even thicker layers of solid ice, which proved somewhat difficult to get through. And other ways to interrupt the mundane, we found polar bear tracks up on the ice sheet, about 170 miles from the nearest ocean. He was just trucking along, and his faithful companion, the Arctic fox, was still in tow, being like, dude, where's the food? You're supposed to kill things once in a while. I eat the scraps. Oh, and we ate really well, because we planned for that. In the end, our route was a little bit different. We did hold to that traverse route that they used to get the supplies to Summit Station on our way out, and then we went up to the north, where we had originally planned to come back this side, but things seemed to be more interesting down lower on the flank of the ice sheet here, and we were going to run out of fuel if we went the other way. So we came back down, hit our fuel cache again, and headed back to Summit Station. Along the way, we put out these 5 automatic weather stations, which are continuing to run out there now, although the albedo, while it's dark, is surprisingly uninteresting. And before we knew it, we were southbound at midnight, heading into Summit Station, and all was over. In the process, we had a pretty successful trip. We did 35 snow pits, 1,100 snow samples, 47 snow casts for grain size that we brought back here to the lab for analysis. Got 1,100 miles of snow radar data. That's sort of an add-on. Made a 240 in situ grain size measurements, 1,090 spectral albedo measurements, so on and so forth, and most importantly, ate all 83 pounds of chocolate. So what did we learn from all this? Well, there's a few different things coming back now. The automatic weather station data is streaming in. We've got a whole bunch of different plots that I have not analyzed yet, and we'll have to get into looking at that. We've got air temperature coming back, shortwave radiation coming in, shortwave radiation going out, calculations of albedo from those, net long wave out. That's all stuff I need to work on this winter. What's actually been addressed so far are this original idea. Black carbon, was black carbon what caused the melt on Greenland in 2012? So we've analyzed the samples with our collaborators for black carbon concentrations, as well as dust. And we don't actually analyze for dust per se, we analyze for tracers that are associated with dust, calcium and magnesium. And then we analyze for some other ions that would indicate the source of the black carbon. If we had nitrate, it would, actually that should be ammonia, I don't know where that came from. It should indicate burning. If we had sulfate, that should indicate that the black carbon was from man-made sources. And ocean influence could be indicated by these sea salts. So is it happening, is what we hypothesized, and others hypothesized about the 2012 melt true? Well, first plot came out. This is the concentration of black carbon. And it's cut off here, but it's in parts per billion. And then we normalized the sites. So the amount of snowfall at each of the different sites is different. You can have as little as 13 centimeters of water equivalent at our sites way north on Greenland, or as much as 1.5 meters of water equivalent at some of the sites along the coast by Melville Sound. So we normalized it so that this is a year of accumulation. And what we can see is here's where we showed up. This is May of 2013. A year back would be the middle of the summer in 2012, the time when the melt happened. And we do have some outlying black carbon concentrations here, but this is a messy plot. There's just too many data points. In here, there's 1,100 data points on here. They're just all on top of each other. So let's average it out. And I've flipped the axes here. We've got concentration of black carbon in parts per billion here, depth in years of snow accumulation here, and 1 year prior to when we were there. Wow, that looks pretty convincing. We've got a black carbon peak that's a lot higher than what we're seeing in 2013. Well, that's good for the theory. And then, the theory was also that it came from biomass burning. And here we've got the right tracer here, not nitrate. We've got ammonia. And we've got a correlation between the black carbon concentration and the ammonia concentration. A couple pesky outliers, but it was not too bad. It looks like the more black carbon we have, the more ammonia we have. It would seem that that's somewhat well correlated. It probably is derived from biomass burning. So nature paper, let's do it. No, you don't get to do that. The problem here is that if we go back here and look at this, it's 2.5 parts per billion. And remember what I said at the beginning of the talk, which was 20 parts per billion of black carbon, in round numbers, lowers the albedo by about 1%. We've got 2.5 parts per billion, not 20 parts per billion. And so that's going to lower the albedo well less than 1%. And it's pretty hard to conceive of where this black carbon layer made a significant enough change to cause melt all the way up over the Greenland ice sheet if the albedo, if we model the albedo, comes out to around a change of 0.35%, less than a watt per square meter. It's just really not enough to have caused that warming there. So then, okay, we got black carbon. It did come from forest fire and activity that was enhanced, but it's not enough to have caused it. So, but we still need to explain, we did see these albedo drops, and how big are these albedo drops? Well, compared to a normal year, and let's put a normal year right in there someplace, we're somewhere in the 5 to 7% lower albedo range. 0.35% is not enough to explain that. So we've got to bring in the other possibility, which is that the grain size changed on the surface of the ice sheet. And that's very easy to expect. It was warmer that year. Grain's metamorphosis happens faster, and that could have lowered the albedo. Okay, but we're not ready to give up the black carbon thing entirely yet. So we just need to make a more complicated feedback cycle. Perhaps what actually happened is you have this black carbon. It makes it just a whisker warmer. Just enough warmer that the grain size starts to grow. And then once the grain size starts to grow, it gets to grow even more. And because it's warmer, it grows even a little bit more. And as the sun hits those larger grains, they grow even faster, and you get some sort of a feedback cycle. Now, there's a couple of models out there that try to work with this cycle of how grain size grows, and they're universally kind of crummy. Sorry to the people who've made them, but there's not a great understanding yet of what influence a very, very tiny amount of black carbon would have on grain size growth. And I think it could be possible that this is causing a feedback still, but we don't really know. So let's take a look at some of the other data that we have to see whether we can come up with any proof at all that might be happening. So what we plotted here is the albedo that we measured. Now this is in the 2013 snow, because we can't go back and measure on the ground that albedo of the 2012 snow. That stuff's all buried too deep. The sun's not hitting it anymore. We measure the albedo of the 2013 snow, and at the same time we had measured the black carbon concentration at the surface in concentration and then inventory in the top 3 centimeters. And what we have here is there's a weak correlation. It's not the strongest, but the albedo seems to be dropping as we increase the concentration of black carbon. But it's dropping much more than we would expect it to be dropping from the direct effect of the black carbon alone. Remember, the direct effect of the black carbon should only be dropping it by 0.35% we came up with. But if you believe this correlation, it's dropping it by 2 or 3% over a very small change in black carbon, 0 to 2 nanograms per cubic centimeter. So that there's something here that this can't be caused by, if this correlation is true, it can't be caused by the direct effect of black carbon. We've got some other mechanism operating here. Again, we can do it with the dust tracers, not just the black carbon, and we can see that we also have a correlation where albedo is dropping with increasing concentrations of calcium, calcium being a tracer that would indicate higher concentrations of dust there. And it's also dropping too much. These levels of dust shouldn't be causing a 7% decline in albedo, as might be suggested by those trend lines. But if we take some other things that shouldn't be absorbing sunlight, we don't have this correlation. So we take nitrate concentration, and it's pretty much flat. It doesn't really seem to have any correlation whatsoever with albedo at the sites that we measured. It's kind of funny here. So you can come up with one of two hypotheses here. One is that the snow metamorphosis is in fact faster due to heat absorption of the black carbon and dust particles, and there's some albedo amplification causing that trend in albedo versus concentration to be stronger than it should be from the direct effects. So there's an indirect feedback of these contaminants on the ice sheet. The other one's a lot simpler. You don't need to invoke any fancy metamorphosis. You could just say snow metamorphosis was enhanced when it was warmer. When is it warmer on the Greenland ice sheet? It's warmer anytime you're moving warm air masses up over the Greenland ice sheet. And you know what those warm air masses from outside probably contain? Contaminants. And you could probably come up with a very strong correlation between the times when it was warmer and air was moving over the ice sheet and the times that you had contaminants getting deposited on the ice sheet. And while the two are correlated, it may not have anything to do whatsoever with the albedo decline that black carbon was there at the same time. That's kind of where we're at right now. We need to figure out which one of those hypotheses is true. We just got a micro CT scanner that's sitting in the warehouse waiting to be set up out at CRREL, and I think we have the possibility to do some experiments to see whether grain metamorphosis is enhanced by having a very, very small amount of black carbon in a sample. And hopefully we'll get some funding to do some laboratory studies of that. Back on Greenland, we also said that we took those 10-meter temperatures. And I wanted to talk about this part of the project too, because I think this is pretty neat. I've had an awful lot of fun working with this gentleman, whose name is Carl Benson, and he was on the Greenland ice sheet in 1952, 53, 54, and 55 in some manner or another. And he did this traverse route here and wrote a very long report on it that was some of the best work that's been done on the Greenland ice sheet. It was very, very thorough, and it's really started the study of ice sheets as a stratigraphic body. The idea that you can look at it as if it were sedimentary rock and you can go back in time by going deeper into it really comes from his work. So very important pioneering work. And one of the things he did along this route was to take temperatures at 10 meters down into the ice sheet. And we replicated that. But it's been super fun talking with him about the differences between the way we do things and the way he did things. And the thing that's the most mind-blowing to Carl, and Carl's still alive, he lives in Fairbanks, Alaska, he's in his late 80s, and he still enjoys doing science, which is amazing to me and very inspirational. The thing he finds most incredible is that we have a box that's about the size of this thing that tells us where on Earth we are with very, very high precision. He can't get over that. That's just crazy to him, because they used theodolites and sextants, which we decided to take one along on our trip just for fun, to measure their location as they moved around on the ice sheet. And they needed to have They also did altitude, so they needed to have one of their vehicles staying stationary at all times to account for atmospheric pressure changes, while the other one moved to the new location, and then the other one switched to monitoring atmospheric changes. This is a huge process. They had 2 guys navigating all the time. They had a big gyro set up on top of their vehicles to aid in dead reckoning navigation. This was like, it was like about 40% of our effort went into just keeping track of where we were. Nothing beyond that. And they did an incredible job. Their sites were within about 1/10 of a mile of accurate positioning on the ice sheet. We were within 2 or 3 miles when we tried this. So here we are, we're drilling these holes 10 meters down on the ice sheet, sticking some thermometers down there, seeing what the temperature was. And here's a quick plot of the results from that. There's temperature on this axis, 10 meters down into the ice sheet. And here's our sites across the bottom. This is the sites that are going up the spine of the ice sheet right here. And then here's where we turn westward and go down toward Thule. And that's the only part of the transect that we're replicating what CRREL did. His temperatures are in black diamonds, or sorry, black triangles, and ours are in red squares. And I guess what we can see here is that up high on the ice sheet, more or less the same as when CRREL was there. This isn't that accurate of a method. Let's not get carried away with ourselves. The temperature really hasn't changed. But as we go lower on the ice sheet, the temperature has warmed, and by an increasing amount, the lower we get on the ice sheet. To the point where by the time we're down at about 1,400 meters on the flank of the ice sheet, it's warmed 5 or 6 degrees Celsius, which is a big warming in a time period when the global mean temperatures increased by about 0.6 of a degree Celsius. Anytime you see warmings of 10 times that, it's something to get your attention. We have to understand, though, what we're measuring here. The concept that CRREL went with was that the 10-meter temperature is representative of the mean annual temperature at the site. And that's only true under very, very specific conditions, and that's particularly when the snow is dry. When the mechanisms for moving heat down into the snow are the same as the mechanisms for moving heat back out of the snow. And that would be in a dry snow, there's conduction moving heat down in, and there's conduction moving heat back out. In a wet snow environment where you have percolation, where water's melting on the top and running down into the snowpack, that water moving down in is taking the latent heat of melting down with it. And there's no parallel process that moves heat back out during the winter. So that could make it so that the temperature isn't actually the mean annual temperature. So interpreting these, we need to be careful about that. But here's the plot of the warming. Again, up high on the ice sheet, not much change. The margin of error of this measurement's about 1/2 or 3/4 of a degree, so we can't say much up there. But lower on the ice sheet, big warming. And so the question would be, was what we're seeing caused by an increase in percolation on the surface of the ice sheet, or has there been changes in surface temperature on the ice sheet that are sort of the same order of magnitude as the changes that have been seen in West Antarctica, like the fastest warming places in the world? So we had a hard time figuring this out because we don't have temperatures up on the ice sheet, mean annual temperatures from stations operating up on the ice sheet year-round. But there's a couple things we can do. One is we can try and think of, we can use the stations we have, and we have a station along our route that was up here high on the ice sheet, and we can look at the MODIS data. And MODIS has an ice surface temperature product that comes from how much long-wave radiation is being emitted by the surface. It's probably not absolutely accurate enough to be used for this, but because it has a bias for cold temperatures, you can only actually see the surface when there's no clouds there. And on clear days, as we know from around here from the couple days ago when it was -21, we have a lot more long-wave radiation going out to space, tends to get colder. And so if we were only sampling the surface on those clear days, we're going to have a cold bias. MODIS has a cold bias in its absolute temperature. And also they have some trouble determining whether there's thin clouds in a place or not. And the tops of thin clouds can be a very, very different temperature than the ground below. So in absolute terms, I don't think I could use that data for this project. But what I can do is take the MODIS temperature gradient with altitude or elevation on the ice sheet. And one thing that's been shown in a lot of past studies is that on the ice sheet, the higher you go, the colder it gets, and it's pretty uniform. And so here I took a a 60-kilometer wide section of pixels along our route from high on the ice sheet to low on the ice sheet, plotted them all up, and you can see they behave pretty nicely. It gets colder, and there's a trend line through it, and so we can use this trend line to say the gradient, if we have a temperature here, we can extrapolate it down to find the mean annual temperature on the surface using this gradient, even though the MODIS temperatures are actually about 5 degrees colder than the temperatures that are observed right here. So we just take those MODIS temperatures, we shift them by the offset, and now we have a reasonable representation of what the mean annual temperature was at all the sites down along. Before we get to looking at that any further, I want to talk about something else CRREL did. Well, CRREL was a pretty insightful guy. He took these 10-meter temperatures along the transect that he did that was like this, and he kind of looked them over and decided that he thought he could figure out what the temperature was anywhere in Greenland based on them. And he made a two-term model. One term was elevation, and he made a linear fit to his temperatures on the east-west legs so that he could do a gradient of temperature with elevation. And the other one was latitude, and he did a linear fit on the north-south leg of his transect. And this is Benson's model applied to the Greenland ice sheet, and this is the actual observations from the MODIS product in 2012 with a, however many hundreds of millions of dollars product later. Benson did pretty good for a two-term model. So clever guy. So this is getting back to that temperature gradient that I was talking about. We started with observed temperatures here, and that's the purple line here. And then we had a lapse rate with elevation going down to here, and so that should be representative of the mean annual temperature. We also have a paper from 1987 where somebody did a meta-analysis of a whole bunch of weather stations that were on the ice in the 1950s. That should be the mean annual temperatures in the 1950s at the surface, and that's the blue line. Very, very similar to the purple line. So here's Benson's observed 10-meter temperatures are the red dots here, and we can see that his temperatures were reasonably representative of our best estimate of the mean annual surface temperature. In blue here is the 10-meter temperatures that we measured. They're very close to the mean annual surface temperature high up on the ice sheet, and as we go lower down on the ice sheet, they deviate from the mean annual temperature by an increasing margin. What does that tell us? Anybody? No? It's warming above the mean annual temperature. Is our warming caused by a change in the mean annual temperature at the surface or an increase in percolation? It's caused by an increase in percolation. Because if there was a change in the mean annual temperature, one of these two lines should have changed to be way up here. And then we wanted to figure out, well, is the increase in percolation, there was this big melt event in 2012. Are all we measuring is that it melted a lot in 2012, which wouldn't really be a very interesting conclusion. And so Gifford and Thomas here in the room were able to provide 3 more temperatures, 10-meter temperatures, that were taken in the general area of this transect, and I plotted them again versus elevation. And they also deviate from the mean annual temperature expected at the sites by a considerable amount, showing that percolation's been an important part of the temperature regime on the ice sheet for longer than just that 2012 melt event. So this means that melt has been moving up the ice sheet, and that's, you can look in Benson's descriptions of his pits. He dug down and he sees no melt of evidence in the pit walls. I dug down in the same place, and I see evidence of all sorts of percolation coming down in the walls of the pit. Melt is moving up the ice sheet, but it doesn't seem like the temperature of the ice sheet increased all that much. Remember, if we go back here, these two lines of the mean annual temperature at the surface are basically the same. And we can also see this from someone else's data. Humphrey et al. Published in 2013 along Benson's southern transect a series of measurements of the 10-meter temperature, and they just barely overlap with the tail end of what Benson measured. Here's the mean annual temperature at the surface. There's Benson's measurements in red dots. They agree with the mean annual temperature pretty nicely. And there's a deviation from the mean annual temperature that increases more and more and more as you go down. and then reaches a maximum and then starts decreasing. So there's a little bit of percolation delivering heat to depth here. There's more percolation here, lots of percolation there. Here, all of a sudden, there must be less percolation. But the lower you get on the ice sheet, the more it ought to be melting. So there should be more percolation there. What's actually happening here is that some of that meltwater is not refreezing and delivering its latent heat into the ice sheet there. It's running off and going into the ocean, taking the heat with it. So this is actually the runoff line. That's the limit on the ice sheet, where you start producing net water that runs out of the ice sheet and ends up in the ocean. And just by monitoring the temperature and a difference between that and the mean annual surface temperature in a transect with elevation, you can determine where the highest point on the ice sheet that's actually contributing to sea level rise is, which I think is a pretty neat measurement, actually. And we talked about this idea that it wasn't just from the 2012 event. When we dug back down, there was all these layers of percolation that were overlapping and on top of each other at many of the sites, and they included 2010 and 2011 melt layers. So it wasn't just, 2012 was the only season that melted high up on the ice sheet, but in 2010 and 2011, it was certainly melting a lot higher than when Benson was there on the ice sheet. We've done a bunch of modeling to see how this would play out, to try and figure out whether a single year's melt event would cause the amount of warming that we saw, or whether we need multiple years. And so here's a single percolation event using all the conditions at one of our sites low on the ice sheet. And what you see is it warms it, and it's really hard to see for how long. But if I zoom in at just those deeper down areas between 8 and 12 meters deep in the ice sheet, you can see that that warming plume that comes down lasts for a while. It lasts for a few years before it dissipates from that one-time percolation event. And so if we had a percolation event in July of one year and we show up the next May, we would actually be at the peak influence from that percolation event. But 2 years later, we'd still see 85% of the influence of that, and 3 years later, we'd still see 65% of the influence of that melt. So when we actually modeled this out, at this site there was 3.3 Celsius of warming, and the most we could get by making some pretty optimistic assumptions from a one-year percolation event was 1.7 degrees of warming. So we think the percolation has been a multi-year accumulating impact on the temperature at depth. So getting back to this idea that this point is the runoff limit. That's the highest point on the ice sheet that water is going to run down and actually impact sea level. And we can determine that based on the difference between this mean annual temperature and the temperature at 10 meters. What this would suggest, looking at the fact that this little tail here has changed since Carl Benson's time, is that the runoff limit has moved up the ice sheet a little bit. Again, it's moved up the ice sheet, if we believe our temperature data, without an increase in the mean annual temperature, at least high on the ice sheet, and probably without much increase in mean annual temperature low on the ice sheet. So this is sort of the temperatures we're measuring in that regard are sort of a status report on how close we are to creating net runoff. If we go back to this one, we can see where is this? This is when we get very close to zero. And you can look through a lot of temperature data that's been taken in glaciers all over the world and find that the runoff limit coincides pretty regularly with where the temperature at depth gets up close to 0 Celsius. Why is that? Well, if you have water percolating down into the firn and then percolating through the firn to get running off down to the ocean, you need to have it not refreeze right away or it doesn't flow very well. And so you need to have temperatures that aren't really cold that are going to refreeze it down at depth. So this runoff limit, we can basically define that as the time at which the 10-meter temperature gets up pretty close to 0, so where you can keep liquid water at depth and have it flow for a long period of time. If we look at our temperatures, even though it's way warmer than it was in Benson's time, we could say that, hey, we're nowhere near creating melt here that's actually going to end up down in the ocean. Everything that melted here refreezes and stays up there. Who cares about it? It doesn't actually influence sea level rise, so that's not that important. But then we can take the model and mess around with it. So we can mess around with it and say, what if we increase the amount of melt that occurred at that site to the amount that occurred the last 3 years the average of the 2010, 11, and 12, from us digging a pit wall and looking at how much liquid water was in the side, has refrozen in the side of that pit. And what if we continued that for a long period of time? What if that pulse of heat just kept happening year after year after year and accumulated down in there? Well, you get a temperature rise, and this is if we use 12 centimeters of water equivalent. A temperature rise of a few degrees, 6 or 7 degrees. Okay, but what happens if we increase that? How sensitive is it to how much water is percolating down in? What if we put 17 centimeters of water down in? We find that it's very, very sensitive to how much melt you allow to percolate down into the ice sheet. We go from a warming after 20 years of, 6 or 7 degrees to, we get right up to that temperature where we can produce net runoff at the site, which suggests that it doesn't actually matter what the mean annual temperature is. It matters what the temperature is during those couple weeks during the summer when the melt occurs. If you can produce just a little bit of melt at all these sites during the summer, you'll actually be able to produce net runoff. And I'm going to argue at some point in the future that we need to be measuring temperatures in the ice sheet a lot more regularly to understand the health of the ice sheet and how melt is moving up the ice sheet, to understand what the future contributions to sea level rise are. Because here you can see that based on this temperature rising, you've got a pretty long warning actually. A 20-year, you can see how much it's moving up this curve and how close you're getting to producing net runoff at that elevation. So this year we're getting ready for our second field season. What we're going to be concentrating on this year is trying to understand the spatial variability of that black carbon that we measured this year. One of the problems we had with our data this year is that, well, Mary Albert's group measured black carbon too up at Summit Station. They measured a pretty high concentration at Summit. We didn't. We measured a low concentration at Summit. 50 miles from Summit, we measured a high concentration. 50 miles beyond that, we measured a low concentration. 50 miles beyond that, we measured a high concentration. What we think is actually happening is that the black carbon is distributed around on the surface by blowing snow, and that the concentration where Simone is sitting right here in the front row might actually be different than where I'm sitting right here. And so we want to do a lot more sampling to try and understand what the small-scale spatial variability is. And we also want to do a better job of differentiating man-made black carbon, Arctic haze, low on the ice sheet, which would be associated with sulfates, from the biomass-derived black carbon high on the ice sheet. And we're going to be measuring more firn temperatures and things like that, and tracking specific plumes from specific wildfires onto Greenland. But really what we need to do is figure out whether black carbon is that important at all. When we first wrote this proposal, I was ready for this I don't like the black carbon thing that much. I wanted this to be, black carbon really isn't important, and this really proves it. And I think we actually still have a credible piece of work that needs to be done here to determine how important black carbon is on the Greenland ice sheet. So we'll be going back and we'll be doing a little bit of a artistic route to try and cover as much area as possible in this western flank of the ice sheet. There's probably some people in the room that would like to send things along with us. We'll probably be willing to do that depending upon how heavy and ridiculous they are. And yeah, that's kind of what I wanted to talk about today. I was told, in addition to talking to you about things science related, that I was supposed to share profound thoughts about what it's like to be an IGERT who's graduated and gone out into the workforce for 2.5 years. And I'm not a very profound person, but I decided I would come up with one wordy slide for you. So this is a change of gears from science stuff. But I like to think that the system is set up in a way, I don't really entirely like it, but you're supposed to do a lot. It's a very individualist system. You write your own grants, you get your own funding, you try and do work. Your name is tied to your publications, and your worth is tied to that. And so in some ways the system is set up that you're your own city-state, and you need to do very, very well for yourself in order to do well. And so the first part, and not necessarily in this order should they be done this way, is that you need to do the things that make your city-state really strong when you get out. And those would be to write efficiently. 80% of my time is spent writing. Writing proposals, writing papers, writing nice emails to program managers, writing. That's almost That's the vast majority of what I do. And along with that, as a corollary, you'll never have as much time to tinker with microcontrollers or whatever whatever you want to tinker with. You'll never have as much time to tinker as you do now. So tinker now. Be prepared to focus on a couple of things. One of the great mistakes I think I made coming out was that I tried to do 4 or 5 major different project areas. I mean, some of you know me for doing sea ice work. Now I'm driving around Greenland. I also have a permafrost project in Alaska. That wasn't a very good idea. It's good to have a couple of different areas, but what you end up realizing is you can't leverage one thing off of another if you've got too many different things going on. You can't use the same equipment. You're not in the same part of the world. You can't double sell the same model to 2 different projects. And I think that's actually an important piece of advice. Think about what you want to be doing, what your split between fieldwork and homework is, things like that. It takes about a 2 to 3 year lead time to change what you're doing. I moved all my focus up to Alaska a couple years ago. Some of you might know that I now own a farm in Norwich. That was awkward. Trying to rearrange something like that, if one so desires, is actually a slow process because you've written all these grants, got them funded, and have to go through the life cycle of those grants. Any realignment takes a little while, so think about what you're doing. Along those same lines, a couple different things. Don't short sell yourself. I wrote a couple of proposals with some senior PIs where I put a month of my time on and put 3 months of their time on. I do most of the work. That's a terrible idea. Don't do that. Sell yourself for what it costs to do your work. And the last one there, don't be too desperate about getting money. There's a lot of good program managers out there. They see you're a young PI. If you come up with good ideas and you're going to do good science and it's stuff you're excited about, you're going to do just fine. I wrote a couple of proposals where I was like, oh, that's easy money. I'm going to run off and do that. And I didn't really want to do that, but I was too nervous about getting the money and making sure I was covered and things like that. Don't do that. It's not a good idea. And use the telephone. Learn how to use the telephone. It's much quicker to resolve a lot of complicated things and not have misunderstandings if you call somebody rather than email. And then the second part of this, so that's your city-state. How do you develop strong alliances with other city-states? Because you cannot exist as your own city-state, no matter how sweet you are. And I think one of the most important things, and I put it first on purpose, is develop a network of a few, 2 to 4 arbitrary number, of collaborators that you can trust absolutely unconditionally. These are people who you can send money to when you're flush. They will send money to you when you're short. These are people who will really help you out and who don't have an ego that's competing with your ego. It's really important. You're going to be short on money sometimes from grants. You're going to be flying high other times from grants. These are the people who you work with that even out to make it so that you have a statistical sample of grant writing, which you can't on your own. Develop a network of other collaborators that you, to use the new parlance, trust but verify. It's really important to have tons of people that you work with, but they don't need to be so unconditionally trusted as that little core group. Talk to your program managers in person. Don't try not to make it too awkward that you're just following them around the room like a sick puppy, but find an excuse to talk with them, see when they're available at meetings and things like that. Start conversations with something that you did that's interesting that you're excited to tell them about, not a problem. Because these are just people. They're just going about their daily life, and they don't want to hear about another problem. Eventually, if you have a problem, you can talk to them about it. But be an excited young scientist. They love to push excited young scientists forward. And also share some life details. You know which ones not to share, but share some. Let them know you're a person. Learn something about them. Ask about their kids when you call them. These are important things. The program manager, as much as I thought they were for the first 6 months or a year, was like on some high pedestal that was like the king that you grovel at their feet and kiss their rings and things like that. They're just people. And the more you can make their job fun, the more they're going to make your job fun. Make sure that wherever you go to work, someone's prepared to invest in you. Monetarily, time-wise, whatever. This is important not just because it's easier to get started if someone's going to offer you a year of salary to start with and a bunch of toys to play with, but because they're tying their success to you. Somebody's going out on a limb to get some money out of the central pot and give it to you. You're now their project. If you fail, they failed at picking the right person. They will help you additionally along the way. That's really helpful. There's many ways that this can happen. All of you know that Don Perovich has been very, very good to me. He is the someone who's invested in me, and it can come in many different forms. It can be the institution, it can be an individual, it can be a group that you're going to collaborate with, but I think it's very important to have that. Have fun, be fun to work with, deliver on time, respond rapidly, make collaboration easy for others. If people send you emails and they get to your bottom of your inbox, it's going to be bad. I am very guilty of this. I'm trying. I understand that it's better to do this. Many of the things on this graph, I won't argue that I'm doing. I'm just noting that they should be done. And try to be the dumbest person in the room. Try and get yourself surrounded by people who know more than you do. It's super intimidating, especially when your ego and your self-worth is tied to being a smart person as a scientist. It feels really bad to be the dumbest person in the room, but you can learn an awful lot that way. I'm still not comfortable doing that, and I'm really trying to do that a lot more. So there's my profound thoughts about being 2.5 years out. I think that was a lot more profound sounding than I have any idea what I'm doing. I have a daily feeling that someone's going to discover that I'm actually a fraud and I'm not doing anything at all. But that's that. Anybody have any questions about the science here or about life as a scientist?
Yeah, I was just curious about with the snow pits, when you normalize them, how did you do the age depth scale?
It was actually really easy to do where July of last year of 2012 was, because there was a melt layer. And so what we actually did for those was oversimplified. We did a assumption of for that plot was just a linear snow accumulation, which anybody could argue is not correct, but we didn't have any data better than a linear snow accumulation at most of the sites. You could see that various snowstorms had happened, but when they actually happened would be a little bit hard to say. But the 1 year ago time frame, boy, you could nail that super easily in the stratigraphy of the snow pit because of that melt layer.
But wouldn't the melt have percolated down to some extent?
Yeah, but the surface grains that were turned into melt grain clusters could all be seen. And you have the percolation tubes, the water going down, but that layer that had been on the surface was very, very easy to pick out. Now, whether the black carbon went down or whether the ions went down with those percolation tubes is a very, very interesting question. And we did a lot of sampling, or a bunch of sampling, to try and explore that a little bit. And the answer is kind of a mixed bag. Sometimes the highest concentration was on the surface, and then I would go down and I'd find one of those layers where the water had percolated down and refrozen. And I'd take a place where there was refrozen water, and in the same layer, horizontally from there, I'd take snow that was at that layer but didn't have percolation come into it as sort of the control. And we saw everything. Sometimes we saw enhancement coming down. Sometimes we saw actually a dilution effect where the water coming down would have been cleaner. I think it's probably a lot the same as what Jack Dibb's seeing here in New Hampshire, which is to say, for some part of the melt, it sits on the surface and accumulates, and at some point it starts to flush down with the percolation water. And I don't think we had enough information on what sites had a little bit more or a little bit less melt, or what the intensity of that melt was to sort that out.
I wonder for your relation between black carbon and albedo and like the dust, if you consider the elevation effect, because we know that there, like just take dust for example, there's a huge elevational gradient of dust with much higher at low elevations, lower as you go up. You'd expect the same for grain size and therefore albedo. So could that?
We actually plotted the calcium tracer concentration against elevation on our route and did not find a strong correlation.
Because we see, like on the grid traverse, GIS data shows
From the 2010,
yeah,
or 11 or whatever you guys are there. We didn't see it in 2000.
Because that would explain too the difference between the dust versus like the ammonium, which we don't see. Because the gaseous phase, we don't see as much of an elevational gradient with those versus like dust. And I don't know black carbon, I've never.
Yeah, we saw, the only thing we saw a strong elevational gradient for was the sulfate, which would kind of argue that the lower elevation was influenced by Arctic haze, and higher up you didn't really get the Arctic haze. And the sulfate was strong in the winter at the lower elevations, as you'd expect from the Arctic haze. none of the other stuff showed a very strong gradient with elevation, which is a little bit surprising. We also probably, on the east-west elevation transect portion of that, there's only 7 or 8 pits. So there just might not be enough data to see some of that.
So I was wondering, what do you think causes the greater amount of variability in albedo at the lower concentrations of black carbon? Because in the graphs that you showed, the variability also decreased along with the mean.
You looking at these graphs?
Yeah.
So at
the
lower.
low black carbon concentrations, you're measuring much more variability in albedo than you are in higher concentrations.
Yeah, although we also have a lot more samples here. There's only 2 samples out there, so that might just be an illusion of the graph. I mean, if you fired 10 more samples out here, I don't really know whether we would get higher scatter or not. And you can also see we're having more variability in the near infrared. There's 3 wavelengths on these plots, which I should have explained. Up in the top right, there's the key. So you've got a blue color wavelength, 390 to 410. You've got a green wavelength, 550 to 570, and then a near infrared wavelength. And you can see a lot more scatter in the near infrared. Near infrared is where we see the effective grain size being the strongest, which would argue that a lot more influence is coming from grain size, perhaps, than the black carbon.
It's my understanding that the bulk of the black carbon in Greenland right now is believed to originate from outside of Greenland, North America, maybe parts of the former Soviet Union, burning and so forth there. But there are some massive mineral projects planned in Greenland that conceivably could end up as a byproduct generating substantial black carbon from diesel and other engines there. How would they be positioned with respect to the ice sheet and the likely movement? For that to be
I guess I don't know too much about what's planned. The only one I'm really familiar with is the aluminum smelting plant that they're talking about putting in, and that would be runoff of hydroelectric power, which would presumably emit very, very little black carbon. Of course, I'm sure there'd be diesel trucks moving bauxite around and things like that, but I guess I wouldn't suspect that would be a massive pollution emitter, say as some hard rock mine might be a bigger pollution emitter. I'm not aware of any studies that are looking at that, but there very well may be. I think one of the other things that people are looking at is increases in Arctic shipping, because that would produce black carbon from dirtier oils that are burned in heavy ships in an area that's more conducive to transport, certainly to the Arctic sea ice and possibly also to Greenland. But as far as the mineral development around Greenland, I guess I'm not the right person to ask.
Give you one more quick question.
Thomas, from your original route, the one that was east of the divide, in the northeast ice stream area,
Yeah.
you still have caches there?
No, we ended up putting the cache just a little bit south of Nîmes. You hoping to use some of our gas.
All right, well, let's thank Dr. Polashenski.